Okay, so then here's my second graph. Can I fit all this here? Yeah. So again, I could talk about this, but eventually stop and draw it. I notice I have a flat point here, so that's a critical number. E is a critical number. And here the derivative is undefined. And hopefully you understand why. I can't, at any sharp point, I can't pinpoint what the slope of the tangent line is. It's teeter-tottery. So derivative is undefined, derivative is 0 here. So notice this. I'm not going to talk about it. You can ask me if you want, but sort of makes sense, increasing, etc. Okay, so basically our goal, by just looking at the table information and knowing that the A, B, C, D, E, and G are the only critical numbers, how can you define, or how can you identify the extrema? So you don't get the graph and you just have this. But right now, stop the video and look back at the graph, look at this, and see what the connection is. Okay, and we will reveal that in a second. Okay, so here is one of two theorems for today. And this we've talked about, but it's an actual bona fide theorem. Let f be a function that's continuous on a closed interval, and it's differentiable. That means a derivative exists on the open interval. If the derivative is positive, then for all x in that interval, f is increasing. If the derivative is negative, for all the x's there, then the function is decreasing. If the derivative is 0 for all, then f is constant. So rewind or whatever and listen to me say that again. That's a big thing. But we've already talked about it. If my slope is negative, that means my function is sloping down. Yeah. So the y values are getting shorter, smaller. So the function is decreasing. Okay. Did you figure out my big challenge to you from here? I hope you did, because here is the first derivative test. And this, they will literally say, use the first derivative test to show something. And this is what they expect to see. So I'm going to show it to you, then we're going to do one example. Okay? So you might want to stop and take this and absorb it. These are all the $5 words. Let C be a critical number of a continuous function around C. Now I wrote that, then I wish I hadn't written it that way. The function doesn't have to be continuous everywhere, but it has to be continuous around that value C, a particular critical number C. If it's differentiable in that interval, and maybe not at C, there could be a sharp point, but if it's just differentiable in the interval around C, then three things happen. So this is cool. If the derivative changes from negative to positive at that value, then f has a relative minimum there. If the derivative changes from positive to negative, notice the difference, very important, then there's a relative maximum there. And if it doesn't change at all, so it's positive on both sides or negative on both sides, then it's neither a max or a min. How cool is that? Here's pictures that show what that is. Look, I have a flat spot here. If my derivative is negative on the left of it and then positive, I mean, you can just draw that in the air. Oh, I'm at a relative min right here. If at a critical value, it has to be at a critical point, critical number, my derivative changes from positive, ooh, flat, then to negative, I'm at a relative maximum. How awesome is that? Now, if I am positive, ooh, critical number, and then positive again, this is neither a max or a min. Okay, so I'm going to stop the video here, and we have the example on the next video.